Assalamu alaikum. Hello students. Today we have to solve example number 2.2 of Electrodynamics 4th edition by David J. Griffiths. In this example we have been asked to find electric field at some point P at a distance z apart from the midpoint of a line carrying uniform charge density lambda. That means charge has been distributed uniformly on this line, and we have been asked to find electric field due to this line at a distance z from its midpoint. Let us start to find electric field at this required point P. For this purpose, we will have to divide this line into small charge elements. Then we will find the electric field due to one of that charge element, and then we will integrate that electric field across this whole line, across this complete line. Okay, let us see one of those charge elements. Let's say this is our charge element, this is our charge element. Okay, this is our charge element, and this charge element is at a distance x from the midpoint of that line. This charge element is at distance x, and the length of this charge element is named as dx. This is the length of this charge element. Okay, and the charge contained by this charge element is named as dq. Okay, then clearly the charge density lambda of this charge element will be equal to of this charge element, that will be equal to charge of this element divided by length of this element, that is lambda is equal to dq divided by dx. Okay, now see what will be the electric field at this point P due to this charge element. Then definitely the electric field vector will be away from this charge element, because we have considered that positive charge has been distributed on this line. Then the electric field vector at this point P will be away from this charge element and will be like in this direction. Okay, sorry, let me draw it again. Okay, that will be in this direction. This is our electric field vector and is named as dE. Okay, now remember that there is another charge element for this element that is on the opposite side and at the same distance. Let us draw that charge element too. So this is our second charge element, which is at the same distance x, Okay, so this distance is also named as x, and length of this charge element is also named as dx, and it contains the same amount of charge dq. Okay, now the electric field at this point P due to this charge element will be like in this way, in this direction. Okay, so the electric field due to this charge element is in this direction, and again it is also named as dE. Now let us resolve these two components into their resolve these two vectors into their rectangular components. If I resolve this vector into its rectangular components, then that will be its y component and named as dE y, and this one will be its x component and is named as dEx. Okay, similarly, if I resolve this dE vector into its components, then this one will be its y component named as dEy, and the other one is named as dEx. Okay, now it's pretty clear that both of these two x components are opposite to one another, so will cancel out one another. Okay, so these two components will be cancelled out. because both of them are equal in magnitude and opposite in direction, so we'll cancel out each other. Then the net electric field at this point P due to these two elements will be only due to y components, because y components both are in the same direction, both are upwards. Okay, so if I discuss here the net electric field at point P due to these two elements, not due to the complete line, only due to these two elements, that net electric field dE will be equal to the sum of these two y components, and will be written as definitely 2dEy. Okay, and in the next step it will become what? It will become 2dE sine theta, where theta is this angle. 2dE, let me write it again, 2dE cos theta, not sine theta. Okay, if I take theta, if I take this angle as theta, then y component will be written as 2dE cos of theta. Okay, now in the next step, what is dE? dE is actually the electric field due to this charge element, due to any of these two charge elements. Okay, so will be written as K, the charge of the element, that is named as dq, so K dq divided by square of the distance of that charge element from our point P. Now that distance is named as, let me write it as r. So the distance of point P from any of these two charge element is named as r, so will be written divided by r square. Okay, and what will be the cos theta here? Cos theta will be equal to base divided by hypotenuse, that is z divided by r. In the next step it becomes 2k dq z divided by, it becomes r cube. And what will be the value of r? According to, if I apply the Pythagoras theorem on any of these two right triangles, I will get here r as z square plus x square. So it becomes z square plus x square inside the square root. This is our r, but here we have cube of r, so I will write here whole power 3. Okay, now if I combine this power 3 and this square root, it becomes whole power 3 by 2. That's simple mathematics, you are well aware. Whole power 3 by 2. Okay, now we want to find electric field due to our this complete line, but this one is electric field due to these two elements. So in order to find electric field due to complete line, I will have to integrate across the line. I will have to integrate this expression across the line. That integral will provide me my required electric field. Okay, so let me integrate it. So if I integrate both sides, this dE will become E, and this E is now the electric field due to complete line. Okay, and this will become 2k z dq divided by z square plus x square and whole power 3 divided by 2. Whole power 3 divided by 2. Now, in order to solve an integral, we should have only one variable into the integral, but here in this case we have two variables. The first variable is dq and the second one is x. Both of these two quantities are actually the variables. How? This dq is variable. How? Because if I take this charge element of smaller size, then definitely the value of the amount of dq charge will be smaller, and if I take this charge element of larger size, then the amount of dq charge will be larger. So that means that dq is actually a variable. Now if I talk about x, this is also a variable. How? If I take this dq quantity near the midpoint, then the size, then the length x will be smaller, and if I take this dq element away from the midpoint, then definitely the size of x will be larger. So x is also a variable. But We know to solve an integral we should have only one variable into the integral, but here in this case we have two variables in the integral. So I will convert one of these two variables into other, and it's simple for me, it's easy for me to convert this dq, to convert this q variable into x variable. How? By using this equation I can write dq as dq equal to lambda dx. Okay, so in the next step I'm gonna write here 2kz, and now this dq will be written as lambda dx divided by z square plus x square whole power 3 by 2, and now we have only one variable into the integral. Okay, so we are in position to solve this integral now, but we should also have the limits of integration. What will be the limits of integration? The limits of integration will be from 0 to L. How? The limits of integration are from 0 up to L. How? Because if I take here for limits of integration, you should focus on this variable of integral. The variable of integral is x. Now if I take my charge element at the center, then the distance of that charge element from this midpoint will be 0, so lower limit is taken as 0. But if I take this charge element at any of these two corners, either at this corner or at this corner, then the distance of that charge element from midpoint will be equal to L. Okay, so the upper limit is taken as L. Hope it's clear. Now this lambda is also a constant, so write it down out of the integral. Now let us solve this integral, and then we will put here the values. Now here my integral is I is equal to dx divided by z square plus x square whole power 3 by 2. Now let me solve this integral. I'm not teaching you here the integration. Okay, I'm just simplifying this integral. Okay, to solve this integral we should have x equal to z tan theta, then dx will become what? That will become z secant square theta into d theta. If I put these two values in the original integral, it becomes like z secant square theta d theta divided by z square plus z square tan square theta whole power 3 by 2. After simplification it becomes something like this, 1 by z square, and it becomes integral of cos of theta, that is 1 by z square, and integral of cos theta we know is sine theta. Okay, it is z square, it is sine theta, but theta is not our original variable. We have introduced it for our simplicity. The original variable of integration was x, so we will and also we know that the limits have been defined for x variable, so we will have to convert this theta variable into x variable. So what if I convert this theta variable into x variable? I will have to use this right triangle. Any of these two right triangles can be used. So if I use this right triangle, then according to this right triangle our sine theta will be equal to x divided by r. So I'm writing here sine theta as x sine theta, x divided by r, so it becomes x over r. Okay, and in the next step it becomes like x divided by z square, and what is r? Again, by using Pythagoras theorem for any of these two right triangles, it becomes r will be equal to z square plus x square inside the square root. It becomes z square plus x square inside the square root. Okay, so this is our required integral. Now let me put that required integral into my original equation. This was my original equation, and let me say that it is equation number 1. Okay, Now if I put the value of that integral into equation number 1, it will look like this. It will look like this. Equation 1 becomes what? The net electric field equal to 2kz lambda, 2kz lambda, and the integral is 1 divided by x square root of x divided by, I made a mistake here, x divided by z square, and this is z square plus x square, and the limits of integration were 0 to L. Okay, now this z and this z square, after cancellation it becomes E is equal to 2k lambda divided by z square. Now if I apply these limits of integration 0 and L, it becomes what? Remember that the limits of integration have been defined for x, not for z. Z is constant here in this case. X was variable, so limits of integration were defined for x variable. Okay, so you have to put these limits of integration for x. Now if I apply these limits of integration, it becomes L divided by z square plus L square inside the square root minus, now if I put here 0 for x, it becomes 0. Hope it's clear. Now in the next step, sorry, I made a mistake here once again. This is not z square, this is z, because this z and z square, this z and square have been cancelled out, so this is z only here. Now it becomes 2k lambda L divided by z into z square plus L square. Okay, and in the next step we can write here further this lambda, for you can see here that I can write it k to L into lambda, k to L lambda divided by z into z square plus L square. Now if I multiply the complete length of the line, was given 2L in the statement of the example. If I multiply the complete length of the line by its charge density, it provides me the complete charge distributed on the line. Okay, so in the next step I can write here, instead of 2L lambda, I can write Q. So it becomes KQ divided by Z over Z square plus L square. I am removing from here and let me complete it. So in the next step it becomes like here. Okay, it becomes like electric field is equal to KQ divided by Z into Z square plus L square. Okay, instead of 2L lambda, I've written here Q. According to this equation, you can see that if 2L is multiplied here with lambda, then that will be equal to Q. So I've written here Q. So this is our final electric field due to this complete line at point P. Now let us discuss a special case. If that distance Z becomes very, very greater than the length of the line. The length of the line was named as 2L. Okay, if this distance Z becomes very, very greater than the length of the line, that means if we take point P very, very, very far away from the line as compared to its length, then what happens? Then this happens, that if Z is very, very greater than 2L, then in that case this term Z square plus L square will approximately be equal to Z square. Agree? Now our electric field becomes in that case KQ divided by Z, and inside the square root it is Z square, and after simplification it becomes kq divided by z square. What does this expression tells us? This expression tells us that if we take this point P very far away from the line, then in that case your line will behave like a point charge for that point. Okay, because this is the formula of the electric field for a point charge. K multiply amount of the charge divided by distance from the charge. This z is now distance, because this d is distance from this charge, from this complete charge. Okay, so this is the formula of the electric field for a point charge. So it has been cleared now that if we take z very greater than the length of the line, that means if we take this point P very far away from the line, then in that case that line will behave like a point charge for that point which is very far away from it. Hope it's clear. In the next video we will discuss, I think that will be problem number 2.3. So let's see the next video. Goodbye.